To achieve state-of-the-art on many NLP tasks, this paper converts every language problem into text-to-text format. So the preprint is from 2019 October, but the blog itself was written in February 2020, so just now. The paper is called Exploring the Limits of Transfer Learning with Unified Text-to-Text Transformer. It's from Colin, Raphael, Narang, Shazir, Matena, Roberts, Zhou, Li, Liu from Google. Transfer learning, where a model is first pre-trained on data-rich tasks before being fine-tuned on downstream tasks, has emerged as a powerful technique in natural language processing (NLP). The effectiveness of transfer learning has given rise to a diversity of approaches, methodology, and practice. In this paper, we explore the landscape of transfer learning for NLP by introducing a unified framework that converts every language problem into text-to-text format. Our systematic study compares pre-training objectives, architecture, unlabeled datasets, transfer approaches, and other factors on dozen language understanding tasks. By combining the insights from our exploration with scale and our new Colossal Clean Crawled Corpus, we achieve state-of-the-art results on many benchmarks covering summarization, question answering, text classification, and more. To facilitate future work on transfer learning for NLP, we release our dataset, pre-trained models, and code. The basic idea underlying our work is to treat every NLP problem as a text-to-text problem, that is, taking text as an input and producing new text as output. Similar approaches were used as part of Natural Language Decathlon in 2018 and to test zero-shot learning capabilities of language models read for 2019. Crucially, our text-to-text framework allows us to directly apply the same model, objective, training procedure, and decoding process to every task to be considered. We leverage this flexibility by evaluating performance on a wide variety of English-based NLP problems, including question answering, document summarization, and sentiment classification, to name a few. With this unified approach, we can compare effectiveness of different transfer learning objectives and labeled datasets and other factors while exploring limits of transfer learning for NLP by scaling up models and datasets beyond what has previously been considered. By combining our insights and scale, we obtain the state-of-the-art results on many of the tasks we consider. So there's this reflection section. I'm going to read that one as well. Having completed our systematic study, we wrap up first recapping of our significant findings. Our results provide high-level perspective on which avenues of research might be more or less promising. To conclude, we outlined some topics you think might find effective approaches for further processing. So takeaways. Text-to-text. Our text-to-text framework provides a simple way to train single model on a wide variety of text tasks using the same loss function and decoding procedure. We showed that this approach can be successfully applied to generative tasks like abstractive summarization, classification tasks like natural language inference, and even regression tasks like STSB. In spite of this simplicity, we found that text-to-text framework obtained comparable performance to task-specific architectures and ultimately produces state-of-the-art results for even when combined with scale architectures. While some of the work of transfer learning NLP has considered architectural variants of transfer, we found that the original encoder-decoder form worked best in our text-to-text framework. Through the encoder-decoder model uses twice as many parameters as encoder-only BERT or decoder-only language model architecture, it has similar computational costs. We also showed that sharing the parameters in the encoder-decoder did not result in substantial performance drop while having the total parameter count. By halving the total parameter count. Supervised objectives. Overall, we found that the Denisoc objective, which trained the model to reconstruct randomly corrupted text, performed similarly to text-to-text setup. As a result, we suggest using objectives that produce short tag-rich sequences so that the supervised pre-training is more computationally effective. Dataset. We introduced Colossal Clean Crawled Corpus, C4, which comprises heuristically clean text from common crawl web dump. When comparing C4 to datasets that use additional filtering, we found that the training on in-domain unlabeled data could boost performance in a few downstream tasks. However, constraining to single domain typically results in smaller datasets. We separately showed that the performance can degrade when unlabeled dataset is small enough that it is repeated many times over the course of pre-training. This motivates the use of a large and diverse datasets like C4 for generic language understanding tasks. Training strategies. We found that the basic approach of updating all the pre-trained models parameters during fine-tuning outperformed the methods that are designed to update fewer parameters, although updating all parameters is most expensive. We also experimented with various approaches for training model on multiple tasks. One which in our text-to-text setting simply corresponds to mixing examples from different datasets when considering batches. The primary concern in the multitask learning is setting the proportion of each task to train on. We ultimately did not find a strategy for setting mixing proportion that matched the performance of the basic approach of unsupervised pre-training followed by the supervised fine-tuning. However, we found that the fine-tuning after pre-training on the mixture of tasks produced comparable performance to unsupervised pre-training. Scaling. We compared our previous strategies to taking advantage of additional compute, including training the model on more data, training the larger model, and using ensemble of models. We found that each approach conferred a significant boost in performance, though training a smaller model on more data was often outperformed by training a larger model for fewer steps. We also showed an ensemble of models can provide substantially better results than single model, which provides an orthogonal means of leveraging additional computation. Ensembling models that were fine-tuned from the same base pre-trained model performed worse than pre-training and fine-tuning all models completely separately, though fine-tune only ensembling still substantially outperformed a single model. Pushing the limits. We combined our above insights and trained substantially larger models up to 11 billion parameters to achieve state-of-the-art results across many of the benchmarks we considered. For unsupervised training, we extracted text from our C4 dataset and applied denoising objective that corrupts the contiguous spans of tokens. We pre-trained a multitask mixture before fine-tuning on the individual tasks. Overall, our models were trained on 1 trillion tokens. In the interest of facilitating replication, extension, and application of our results, we released our code, the C4 dataset, and the pre-trained model weights for each T4 variant. So that was the spice of the paper that must flow. I will now go very shortly into more detail, but I have just a couple of minutes. If you like this video, please don't like it and never subscribe. And now I continue in a little bit more detail. Introduction. Training a machine learning model perform natural language processing task often requires that the model can process text in a way that is amenable to downstream learning. This can be loosely viewed as developing general purpose knowledge that allows model to understand text. This knowledge can range from low level, the spelling of the meaning of the word, to high level. In modern machine learning practice, providing this knowledge is rather done explicitly. Instead, it is often learned as part of an auxiliary task. For example, a historically common approach is to use word vectors, Mikolov, to map word identities to continuous representation where ideally similar word mapped to similar vectors. These vectors are often learned through the objective. You can see command to pre-train entire model on data-rich task, transfer to downstream tasks. Pre-training is typically done with supervised learning on large labeled datasets like ImageNet. In contrast, NLP pre-trained unsupervised. Figure 1, a diagram of our text-to-text framework. Every task we consider, including translation, question answering, and classification, is cast as feeding our model text as an input and training it to generate some target text. This allows us to use same model, loss function, hyperparameters, etc. across our diverse set of tasks. It also provides a standard testbed for methods included in our empirical survey. T5 refers to our model, which we dub as text-to-text transfer transformer. So T5. Translate English to German, that is good. It goes to T5, T5 then outputs, das ist good. Cola sentence, the course is jumping well. T5 classifies as not acceptable. Sentence 1. The rhino grazed on the glass. Sentence 2. The rhino is grazing the field. 3.8. Yeah. Okay. This synergy resulted in a great deal of recent work developing transfer learning methodology for NLP, which produced a wide scope of pre-training objectives. But basic idea of our underlying work is to treat every NLP problem as text-to-text problem. We emphasize that our main goal is to propose new methods, but instead to provide a comprehensive prescriptive on where the field stands. As such, the bulk of our work comprises of survey, exploration, and empirical comparison of existing techniques. Our approach is casting every problem as a text-to-text task continues as an additional major contribution. This unifying framework differs from current practice and boasts both simplicity and strong performance. Finally, we also push the field forward by training larger models than have been previously considered. 11 billion. In order to perform experiments at this scale, we introduce Colossal Clean Crawled Corpus, a dataset consisting of hundreds of gigabytes of clean text scraped from the web. Recognizing that the main utility of transfer learning is the possibility of leveraging pre-trained models in data scarce settings, we also contribute our code, datasets, and pre-trained models. So we have a setup, model. The transformer was initially shown to be effective for machine translation, but significantly been used in wide variety of NLP tasks. Primary building block is transformer is self-attention. Self-attention is variant of attention. Rural encoder decoder transformer implementation closely follows the original proposed form, Ashwani 2017. First, the input sequence of tokens is mapped to sequence of bending, which is then passed into encoder. The encoder consists of stack of blocks, each of which comprises of two subcomponents: self-attention layer followed by small feed-forward network. Layer normalization is applied to the input to each component, and the residual skip connection adds each component's input to the output. Dropout is applied within the feed-forward, where the skip connections on attention waits as an input on entire stack. So since the self-attention is order independent, it is common to provide explicit position to the transformer. Original transformer is sinusoidal position embeddings. It's become more common to use relative position embeddings. As part of our study, we examine the scalability of these models, how their performance changes as they have more parameters and layers. Colossal Clean Corpus. Command crawl is publicly available with a web archive that provides web extracted text by removing markup and other non-text content from scraped HTML files. This process produces around 20 terab of scraped text data each month. Unfortunately, the majority of the resulting text is not natural language. Instead, it's largely comprised of gibberish or boilerplate text like menus, error messages, or duplicate text. Furthermore, a good deal of scraped and so on. To address these issues, we used the following heuristic to clean up command crawl, except that we only retained lines that ended in terminal punctuation mark. We removed any page that contained any word like list of dirty, naughty, obscene, or otherwise bad words. Many of the scraped pages contain warnings, JavaScript enabled, some pages with placeholder lorem ipsum text, some pages inadvertently contain code. To the duplicated test, we discarded all inputs but one of any free sentence span occurring more than once in the dataset. Okay, then there are downstream tasks, experiment, baseline. Okay, I got to go. Thank you very much for listening. You made it to the end. Let me know if you have any suggestions or feedback, and please dislike and unsubscribe. And yeah, see you next time. Bye.